Hello! In this video, we're going to derive the center of mass of a semicircle. Now, as you can see, we have a semicircle here with radius A. Now, we expect the center of mass of the semicircle to be somewhere on the y-axis due to symmetry. So, the x center of mass must be 0. So all that's left to figure out is the y-coordinate of the center of mass. And to compute the y-coordinate of the center of mass, we can use the following formula. So the integral of y dm all over the integral of dm, where dm refers to a really small amount of mass in our region. Now, if you recall, we can re-express dm using density, right? dm is just density times the differential area, right? So we're going to go ahead and re-express dm as rho dA. Now, for our purposes, we're going to treat density as though it's constant, which means we have uniform density throughout, right? And that means we can pull out rho to the outside of our integral. So as you can see, rho will cancel out. And so at this point, it looks like we have two integrals we need to evaluate. But really, this bottom integral just refers to the total area of our semicircle. And really, we know that the area of a semicircle is just half the area of a circle, which means the area of our semicircle is just 1/2 pi a squared. So all that's left is to evaluate the top integral. And to evaluate the top integral, we're going to convert it to polar coordinates because, well, we're dealing with a circle. So if we recall, in polar coordinates, dA is just r dr d theta, and y is r sine theta. So let's go ahead and rewrite y as r sine theta and dA as r dr d theta. Now, in doing so, we realize that we're going to be dealing with a double integral because we have two differentials. So this is what we get. But now we have to figure out what our bounds of integration are going to be. And remember, this integral is with respect to r, this integral is with respect to theta. Let's start with our integral with respect to r. Well, really, we're integrating from a radius of 0 to a radius of a. As for our integral with respect to theta, we're integrating from an angle of 0 radians to an angle of pi radians. So now, let's begin evaluating this. And to start, I'm actually going to move this guy into the numerator. If we do that, we're really going to be rewriting this as 2 over pi a squared. So really, we're just taking this guy and multiplying it by what we have in the numerator. Right, and this can be simplified down to r squared sine theta dr d theta. Let's first evaluate our integral with respect to r. Now, in evaluating this integral, we're treating theta as a constant. So really, the integral of r squared is just 1/3 r cubed. So this becomes 1/3 r cubed sine theta. Right, and our bounds go from 0 to a. But since it was an integral with respect to r, I'm going to specify we're going from r equals 0 to r equals a, right? So what do we do with this? Well, we're really just taking what we have here, substituting r for a, subtracting it by this, where we substitute r for 0. So really, this is just 1/3 a cubed sine theta minus 1/3 0 cubed sine theta. Well, that just becomes 1/3 a cubed sine theta. Okay, and since 1/3 a cubed is a constant, we can pull that to the outside of our integral. Okay, now let's immediately simplify this, right? We see that a cubed divided by a squared is just a. So this entire thing is just 2a over 3 pi. So 2a over 3 pi times this integral. Well, we know that the integral of sine theta is just negative cosine theta. Right? And our bounds go from 0 to pi. So I'll write theta equals 0 to theta equals pi. Now, in my opinion, it gets annoying when we have a negative sign here. So what I like to do is I like to get rid of the negative sign, right? And you're allowed to do that as long as you swap these two guys around. So now we're going from theta equals pi to theta equals 0. So really, this is just cosine of 0 minus cosine of pi. Now we know that this is just 1 minus negative 1, which means this is just 2. So really we have 2 times 2a over 3 pi. Well, that just becomes 4a over 3 pi. Or I'll just write 4 over 3 pi times a. So really it's just a constant times the radius. That's it. That is the y center of mass of the semicircle. So this right here is our final answer, right? And 4 over 3 pi is approximately 0.4 to 0.45, right? Roughly around there. So what that means is, to roughly identify where the center of mass of the semicircle is, well, let's start at the origin and move up the y-axis. Well, all you have to do is move up the y-axis about 40% of the radius of the semicircle, and you've identified the location of the center of mass. So yeah, that's pretty much it for this video.